Consider a quarter of circle OAB with radius 1. A green circle is inscribed in the quarter. At the lower right-hand corner, a red circle touches the three sides. Let the radius of the two circles be x and y. Find the radius ratio. To start with, we let the centers of the two circles be C and D respectively. Denote the 6 points of contact as shown in the figure. Now, let's focus on the green circle. Construct the side OC and extend it. Actually, it reaches the point G on the arc. Why is it the case? The key point is the common tangent at G. Let's call it L1. By tangent perpendicular to radius, L1 is perpendicular to both the radius of the quarter OG and the radius of the green circle CG. So the 3 points O, C, G lie on the same straight line. The result is important to work out the lengths of the sides. Now, construct the radii CE and CF. What's so special about the quadrilateral OECF? First of all, angle E and angle F are both 90 degrees. We are also given that angle O is a right angle. Therefore, angle C is also 90 degrees by angle sum of polygon. With four right angles, we can say that OECF is a rectangle. However, there's something more than that. You see, CE and CF are both radii of the green circle with length x. At the same time, they are the adjacent sides of the rectangle. So OECF is actually a square. That means the lengths of all the four sides are equal to x. Let's move on to the right-angled triangle. We make use of Pythagoras theorem, so the diagonal OC is equal to x times square root 2. Now, we consider the straight line OCG. Clearly, OC plus CG is equal to OG. Here, CG is the radius of the circle, which is x. Also, OG is the radius of the quarter, which is equal to 1. So we get this equation. Now, on the left-hand side, we take out the common factor x. Then, we divide the bracket term to the right-hand side. To simplify this expression, we multiply it by the fraction square root 2 minus 1 over square root 2 minus 1. This process is called rationalization. Therefore, the value of x is equal to square root 2 minus 1. Alright, let's move on to the smaller circle. Construct the radius dh, which is equal to y. Then, angle h is equal to 90 degrees. Is there any relationship between the two circles? Let's construct the radii ck and dk, and L2 be the common tangent. So we get two more right angles. That means angle CKD is actually 180 degrees. Therefore, the 3 points CKD also lie on the same straight line. So the length of CD is equal to x plus y. Here, we keep using x instead of the value for convenience. Next, we let P be a point on the green side, so that CF is perpendicular to DP. Therefore, the purple figure PDHF is a rectangle. The opposite sides PF and DH are both equal to y. So the blue side CP is equal to x minus y. Next, we look at the blue triangle. Let PD equals to z. Because it's a right-angled triangle, so z squared plus bracket x minus y whole square is equal to bracket x plus y whole square. We expand the two perfect square terms on both sides. Now, the x squared terms and y squared terms can be cancelled out. So z squared is equal to 4xy. That means z is equal to 2 times square root xy. With this value, let's go back to the purple rectangle. Because PD and FH are opposite sides, so both of them are equal to 2 times square root xy. At this moment, we just need one more triangle to solve for y. Construct the red side OD. If we know its length, then we can set up an equation in y. To do that, let's extend it to touch the arc AB. By considering the common tangent L3, we can see that this situation is exactly the same as the green line OCG. So ODL is also a straight line. Here, dl is equal to y because it's the radius of the smaller circle. For the length of OL is the radius of a quarter circle, so OL is equal to 1. That is, OD is equal to 1 minus y. If we look at the red triangle, then bracket x plus 2 times square root xy whole square plus y square is equal to bracket 1 minus y whole square. Let's expand the two perfect square terms on both sides like this. We can cross out the y square terms. Let's see how to solve this equation with some special tricks. We group these two terms of y to get 2y times bracket 2x plus 1. Next, the square root term is put at the middle. We leave bracket x squared minus 1 at the back. Let's call this equation 1. Indeed, the last term can be simplified. From the value of x, we have x plus 1 is equal to square root 2. Squaring both sides, then x squared plus 2x plus 1 is equal to 2. In other words, x squared minus 1 is equal to negative 2x. Let's call this equation 2 and put this back into equation 1 like this. Now, we can divide both sides by 2 to get a simpler equation. Moreover, let's write the first term y is equal to square root y whole square. Then we can see that it's a quadratic equation in square root y. Here we use another trick. Let k be the constant square root x and u be the variable square root y. Then the equation is u squared times bracket 2k squared plus 1 plus 2k cubed u minus k squared is equal to 0. Indeed, this quadratic equation can be solved by cross method. Now, we separate the first term into u times bracket 2k squared plus 1 and u. For the constant term, it's the product of negative k and k. After cross multiplying, we get negative k times u plus k times u times the bracket term. The two terms ku can be cancelled out, so the sum is equal to 2 times k cubed u, which is exactly the same as the middle term in the equation. Therefore, it can be factorized as u times bracket 2k squared plus 1 minus k times bracket u plus k is equal to 0. That is, u is equal to k over 2k squared plus 1, or u is equal to negative k. Now, we put back k equals to square root x and u equals to square root y into the two results. Then the second one is rejected, because square root sign must take positive value. Eventually, we have square root y is equal to square root x over 2x plus 1. That is, y is equal to x over 2x plus 1 whole square. Rearranging the terms to get x over y. We put the value of x equals to square root 2 minus 1 into the expression. Therefore, the radius ratio is equal to bracket 2 times square root 2 minus 1 whole square. It's really a nice challenge in geometry combining with algebra. Looking for more tricky questions? Check out the next video right here on the screen. I will see you there.